Okay, good morning, everyone. First things first, announcement. Let's see, today is lecture 6. Okay. Announcement about the next homework. It's on mesh current analysis. We will introduce the topic today, but we won't have time to get into the example problem today. The homework was due tomorrow night, so I will extend it most likely by one or 2 days. So we'll cover the little bit of the theory today. We'll go over the rest of the theory and the example problem in class on Wednesday, and then I will make the homework due either Wednesday night or Thursday night. So about 2-3 problems on that homework. Okay, so let's get started. Mesh current analysis is a similar technique to node voltage analysis. Okay, and let's see. Okay, so as I was saying, mesh current analysis is a similar technique to node voltage analysis, but instead of applying node voltages, we are now applying mesh currents. In node voltage analysis, we apply KCL to generate our mathematical equations. The process is still the same, but instead of applying KCL, we apply KVL to generate our equations. Okay. So in node voltage analysis, we assume node voltages, we assign branch currents, and then we apply KCL and express each current in terms of the voltages by using Ohm's law. In node voltage analysis, we apply KVL, generate equations, and then we apply Ohm's law, express each voltage in terms of the mesh currents. If you look at this example right here, it's marked with 3 mesh currents inside it. Okay, so let's first explain what a mesh is, then we'll talk about mesh currents. A mesh is a simple electrical loop. Okay, a mesh is a simple electrical loop that does not contain any loop inside it. Okay, does not contain any loop inside it. Okay, is everybody familiar with the concept of an electrical loop? All right, let's go over that concept first. Okay, loop is basically a closed pathway. Loop is a closed pathway in an electric circuit. For instance, if I write the bottom left corner as node A as an example, and I start going around the electrical pathways and come back to that exact same point, that comprises a closed pathway, and that closed pathway is known as an electrical loop. Okay, but that is not the only pathway. I could take multiple pathways around the circuit and come back to the exact same point. So let's call this as loop 1. Then I could start from A, go around R2, and come back to A. I can call that loop 2. Make sense? Right? There are also other pathways where I could start at A and come back to that same point, and I can call that as, I'm going to call that as 4 for one specific reason, because there are still multiple loops inside the circuit. I can still find another loop like this to come back to A. I haven't even touched on the right side of the circuit yet. But I've drawn out 4 electrical loops just from that single point. If you take a look at these 4 loops, 1, 2, 3, 4, what do we see? 1 is the outer loop, the really big loop. It contains 3 other loops inside it, 2, 3, and 4. There's actually more than 3 loops inside 1. There's loops here, and there's loops all the way going around here, and then it just becomes messy, so I'm not going to go on. But the point is that loop number 1 contains multiple loops inside it. Okay, so it is not considered a mesh. The only mesh that we see in this is loop 4. Loop 4 does not contain any other mesh inside it. Hence, it is known as a simple electrical loop, also known as a mesh. Okay, I'm going to keep this here while we take a pause, and you let me know if you have any questions. Make sense? Right? So I'm going to wipe these out for now. Actually, not for now. I'm going to wipe it out. And you can see identifying meshes is a whole lot easier than identifying nodes. Okay, you find a closed pathway that doesn't have any other closed pathway inside it, and that's a mesh. So in this example, I can identify and write this as mesh 1, this as mesh 2, and this as mesh 3. Then the next thing to do is to assign mesh currents to each one of these meshes. The direction of the mesh current can be anything. You can choose clockwise or you can choose counterclockwise. In the case of this example, there are 3 meshes, 3 mesh currents, and all 3 of them are going clockwise. That is always the direction that I choose. But again, as with node voltages, you can assume any node is a reference node. So it's the same case with mesh currents. You can choose any direction for your mesh currents. It does not really matter. Your analysis will turn out to be correct. So assume a direction and assign mesh currents to each single mesh. And this is also summarized on the next slide. Okay, this is also summarized on the next slide. Again, it does not matter which direction you choose, clockwise or counterclockwise. It does not really matter. But here's the important point. Mesh currents are not real. They are purely theoretical or hypothetical. They do not exist in real life. Okay, they do not exist in real life. They are purely for theoretical purposes. As you go along in engineering studies, even in your own fields, when you do an analysis for any structure, for any machinery, for any machines, you always make certain assumptions. These assumptions are what allows us to actually solve engineering problems. Okay, so it's the same case with electrical engineering. We make certain assumptions. These assumptions allow us to solve for our problems, for our circuit variables. Okay, so again, mesh currents are not real. Mesh currents are hypothetical. They are purely theoretical. They do not exist in real life. If you look at R2 and if you look at R3, R2, R3, and actually also the voltage source VB, all 3 of them share more than one current, more than one mesh current. Okay, if you take a look at R3, R3 is a shared branch, between mesh 1 and mesh 2. So it has 2 mesh currents flowing through it. Okay, but there is no physical basis for 2 currents to flow in the same circuit. So if I look at just R3, what do we see? R3 again is a shared branch. You have I1 that is coming from the top, and you have I2 that is coming from the bottom. which is physically impossible. Electrical current through a resistor will flow because there is an electric potential imbalance between those 2 points, right? If they are both at the exact same potential, meaning the voltage across the resistor is 0, then there is nothing that is going to flow between the 2 points. In order for current to flow, one point has to be higher than the other. Okay, current flows from high to low. So if one end of the resistor is higher than the other, then current will flow from the positive end, the higher end, to the lower end. Right? At the same time, I cannot say that this point is higher. It's physically impossible. Make sense? Right? So mesh currents are hypothetical. They are not real. They do not exist in real life. Semiconductor physics, that's a different thing. We can have multiple currents due to the flow of holes as well as due to the flow of electrons. It's a completely separate thing. We do not get bogged down into the semiconductor physics of things. Okay. Electrical engineering, circuit analysis, current can only flow from high to low. So again, mesh currents are not real. So let's see how we would write an equation in each one of these meshes. Okay. The theory is simple. We have a mesh current that flows through each one of these components. When the current flows, it causes a voltage drop, right? So we sum up these voltages by applying KVL. We generate our equation, and then we express each voltage using Ohm's law. So let's take M1. Mesh 1, when I sum up and I apply KVL, again, if you are used to applying KVL in a certain way, you stick with what you know. Okay? Do not feel compelled to use what I do. So if I apply KVL in mesh 1, I have 3 voltages, VA, VR2, and VR3, which should sum up to 0. Okay, it should sum up to 0. Now, the way I apply KVL is I sum up in a clockwise direction, and I apply a minus to VA, plus to VR2, plus to VR3. Other methods, other students and other professors like to think of the voltage source as positive, and then you keep on deducting voltages around the loop. So you would get VA plus VA minus VR2 minus VR3 equals to 0, which is the exact same mathematical expression. No difference. Let's take a 10-second pause while you think over all of that. Let me know if you have any questions. Yes. We would solve for so the question being asked is, what is the unknown variable? So the unknown variable would be the mesh currents. And once you have the mesh currents, then we can find everything else in the circuit. So we can find the voltage drops, we can find the currents flowing through the circuit, we can find everything else. Yeah. Yes. Yes. Yeah, the question being asked is, what if we choose a different direction for the mesh currents? Then the answer is the signs would turn out to be, opposite than what I have on the board here. But as was the case with node voltage analysis, it doesn't matter which node we choose as reference node. All other nodes in the circuit are measured with respect to that node. So when you choose let's say we choose clockwise, instead of clockwise, we choose counterclockwise, then the voltages would add up in a different way. But then the same direction applies when we get to mesh 2 and mesh 3. And so the voltages would all balance out. Okay, the voltages would all balance out. Okay, so minus VA plus VR2 plus VR3. Mesh 1 is basically this mesh right here. So we have R2, we have VA, R3, and we have I1. So if I was to apply Ohm's law, What is VR2 in terms of Ohm's law? V equals IR. R is R2. So what is the voltage VR2? Yep. R2 times I1. And for VR3, it would still be R3 times I1. But I did see someone shaking their head. Do we agree or disagree? Yes? That is correct. So the observation is that R3 and R2 are both in shared branches. Okay. So we have to account for all the mesh currents in all the shared branches. So VR2, it is correct that it is I1 times R2. That is correct. But we also have to account for I3 and we have to account for I2. So we have to extend that answer to include both I3 and I2. Okay. So all answers are correct. It's just that we have to extend that voltage drop to include I3 and I2. So VR2 should include I1 as well as I2. And I am taking it as I1 minus I2. Sorry, not I2, it's I3. Because we are adding up voltages in mesh 1. Here we are adding up voltages in mesh 1. So I1 would be positive and I3 is negative because of my chosen direction, counterclockwise. It is flowing in the opposite direction. Think of it this way. I1 enters R2 from the left. So it causes a voltage drop plus minus. I3 enters from the right. So it causes a voltage drop opposite to I1. If I chose I3 as counterclockwise, then it would be in the same direction as I1. Then it would become I1 plus I3. Does that make sense? Right? Here, because of the chosen clockwise direction for all three currents, then the shared branch will always have the mesh currents going in the opposite direction. You can take any circuit you want and apply any mesh currents you want. If you choose clockwise directions for all of your currents, the shared branches will always be in the opposite directions. Okay, and you can try that out for yourself. So R2 is shared between mesh 1 and mesh 3. Both of those currents are clockwise, and since both of those are clockwise, it'll become I1 minus I3. When you get to mesh 3 and you add up the voltage across R2, it'll become I3 minus I1. And again, you can apply KVL mathematically, step by step. You will get that exact same answer that I'm saying. It'll become I3 minus I1. And that's why it does not matter which direction you choose for your mesh currents. You can mix and match. You can have one current clockwise, the other current counterclockwise. It does not really matter. When you sum up the voltages, it'll all end up correctly. Okay. So in this case, I have my expression I1 minus I3 times R2, and VR3 would be I1 minus I2 times R3 equals 0. So again, R3 is shared between 1 and 2. 1 would be positive, 2 would be negative. When we get to mesh 2, the signs will flip. So the assumptions that you make at the beginning of your analysis, you have to stick with those assumptions until the end of your analysis. If you change your assumptions halfway through your solution, then it would be incorrect. Otherwise, as long as you're consistent, your answer will turn out to be correct. Does that make sense? Let's take a 10-second pause while you think over that. Let me know if you have any questions. Any questions at all? Yes. Sure. So the question being asked is, why are we subtracting I3? Let me actually draw this out with the visual here on the right side. So why subtract? We have I1 entering from the left. We have I3 entering from the right. Point of entry is? Anyone? Point of entry is always plus, point of exit is minus. Point of entry is plus, point of exit is minus. Because we chose clockwise direction for all three of our currents, I1 or R2 enters from the left. Hence, left is positive. I3 enters from the right. So right is positive. So if we sum up voltages in mesh 1, I1 becomes positive, I3 becomes negative. And the same thing will flip when we get to mesh 3. The same concept applies, but now mesh 3, I3 becomes positive and I1 becomes negative. So the signs flip. Does that answer your question? Okay. Any other questions? Yes. Yes. Yeah. It's not an assumption, because when we add up KVL, that's how it will turn out to be. We could also think of it this way. The answer is yes. You know, if the question being asked is that should we assume that the mesh current in each single mesh that we're adding KVL, should we assume that to be positive? And the answer is yes. But the reasoning behind it is, of course, when we apply KVL and you sum up the voltages, that is the end result. So it's not an assumption, more as a conclusion. Okay. Okay. So let's say mesh 2. Okay, mesh 2. So if we do mesh 2, then I have, what do I have? I have R3 here. I have a voltage source. And I have R4 on the right. So I got plus minus VB, plus minus plus minus VB. And this is R4. This is R3. Now I have current going in this direction. This is mesh 2. And I have I1 coming down. Okay. We have, actually, no, we are almost out of time. Let me write out the equation and then we'll stop there. Okay. I'm going to start by applying VB plus VB plus VR4 plus VR2 equals 0. VB will remain the same. R4 is not shared between any branch, so it will simply be I2 times R4, and VR2 becomes I2 minus I1 equals 0. VB is, of course, the voltage source. We cannot, yes, go ahead. Oh, yes, R3, thank you. Multiplied by R3 equals to 0. So VB, of course, is the voltage source. We are summing up the voltages, so we do not have any need to express it with anything. We simply write VB, then VR4 is not shared, so it's just I2 times R4. R3 is shared. I2 will be positive, I1 will be negative, opposite directions. and hence I2 minus I1. I will go over mesh 2 again in next class. Okay, but think on this. Also, the homework for sure will be postponed. I will extend it by, not postpone, extend it by at least 1 day, if not 2. More likely than not, I will extend it by 2 days. If you have any questions, I will have student hours this afternoon from 1 to 2:30.